So in our previous class, okay, we talked about the idea of specific latent heat, okay, and we find that the heat is the same lah, okay, the heat is the same. So example let's say you heat up a certain material, okay, originally it is solid, and then it melts to become liquid, and then it it boils to become steam or gas lah. So um, so when we provide the heat, okay, of course the heat that we're providing is the same, okay, but the purpose or the function of the heat is different. And so because the function of the heat is different, we have to give different names to the heat. Okay, so what we learned last week, and I hope you got this, is that when there is a temperature increase, when the curve looks like this, there is a gradient over here. Okay, when there is a temperature increase, that means the kinetic energy of the molecules is increasing. So the heat is being used to provide, to give extra kinetic energy to the molecules lah. Okay, and this heat, okay, we call this the specific heat capacity. Okay, the heat is the same. It's just that we have to give it a different name because it serves a different purpose. The purpose of specific heat capacity is to increase the temperature so that the kinetic energy of the molecules can increase. But whenever it flatlines like this, it doesn't mean that the heat is not being provided. The heat is being provided, but there is no temperature increase because the kinetic energy of the molecules is constant. Now, what is happening here, actually, if you can please add this into your module, whenever you see constant temperature and kinetic energy of the molecules is constant, what is actually happening here is the heat is used to break the molecular bonds. Okay, to break the bonds between the molecules. Okay, so whenever there's a flat line here, whenever there's a flat line here, it doesn't mean that there's no heat that is being absorbed. Okay, but it is because the heat is now not used to increase the temperature, the heat is now used to change the phase. Okay, so this one, the phase is the same. I hope you notice this lah, that throughout the whole thing, this is a mistake, as I said, this is solid. Okay, whenever there's a temperature increase, there is no change in phase. Okay, whenever there's a temperature increase, sorry, this is also liquid, there is no temperature, there is no change in phase. But whenever there is a constant temperature, there is always a change in phase. Okay, whenever there's a constant temperature, there is a change in phase. Liquid becomes liquid and gas becomes gas. Solid becomes solid and liquid becomes liquid. Okay, so it is either change in phase or change in temperature. Okay, it cannot be both at the same time. Okay, as I said last week, the most important thing that we have to remember and we have to understand is that heat cannot multitask. It can only do one thing at one time. Either it increases the kinetic energy of the molecules, or it breaks the bonds so that there will be a change of phase. You cannot do both at once. Okay, although you're providing the heat, okay, and we think that, oh yeah, it's probably doing both at once, but in reality, it is not. Okay, and this graph explains why. Okay, actually, if you were to do this experiment and you plot the temperature, okay, you will get about the same graph as well. There will be a period of time where there is no temperature increase. Okay, and you start to wonder, what is happening? Is my ice rosak or is my heat rosak? No, actually, nothing is rosak. There's no temperature increase simply because the heat is now being used to do something else. Okay, and so when we look at the cooling curve, okay, we find that everything is about the same except that in the cooling curve, heat is being released. Okay, so when heat is released, the temperature decreases, kinetic energy of molecules decreases. This one is specific heat capacity. Whenever it is flatline, it is specific latent heat. Whenever there's a temperature increase or decrease, it is specific heat capacity. Whenever there is a flat line, it is specific latent heat. This one is specific heat capacity. Okay, so this is why we only learn this cooling curve and the heating curve after I introduce to you the specific latent heat. Okay, so that you know that in the cooling curve or in the heating curve, both types of heat are involved. Okay, depending on what the purposes is. Okay, so let's move on. So the next activity over here, Astaga, this is already shown to you. Sorry. Okay, so let's compare and discuss this. Okay, so we have wax and ice over here. Okay, wax. I hope you know what's wax. Okay, so at room temperature, wax is solid, and at room temperature, ice is also a solid. Okay, the specific latent heat of fusion. Okay, specific latent heat of fusion is the change between solid to liquid. Okay, kalau solid pergi liquid means heat is absorbed. Kalau liquid to solid means heat is released. Okay, so the specific latent heat of fusion is 2 times 10 to the power of 5 joules per kilogram. Ice is 3.34 times 10 to the power of 5. So, let's have Elvin to do this. Elvin, can you compare the specific latent heat of fusion and of ice and wax?
The ice is higher than the wax.
Okay, very good. The specific latent heat of ice is higher than the wax. Okay, so state the difference between ice and wax in terms of strength of bond between molecules. We find that arrangement between ice molecules is closer. Okay, and the strength of the bond between ice molecules is stronger simply because you need more heat to break it up. Okay, wax only requires 2.2 times 10 to the power of 5. Whereas for ice, you need 3.34 times 10 to the power of 5. So this shows us that ice, okay, the bond between the ice molecules is stronger because you need more heat to break it up. Okay, understand the comparison. It's a very important comparison. Okay, let's look at the second one. Sorry, I don't know what happened. I don't know why this answer came up, but okay, let's look at the liquid one. So water, turpentine oil, and petrol. Look at this specific latent heat of vaporization. Vaporization means it is the change between liquid to gas. Okay, liquid to gas heat is absorbed, gas to liquid heat is released. Okay, so let's compare the specific latent heat of vaporization for water and petrol. Only water and petrol. Vion, can you answer this, please? Assuming that Vion is here. Okay, she is.
Water is bigger than petrol.
Okay, very good. Water is bigger than petrol. The numbers tell us. Okay, so good, good, very good. Okay, I want to make sure that you all know how to compare because it is a important skill okay, in physics SPM. Okay, so state the difference between water and petrol in terms of the strength of the bond between the molecules and the distance of separation. So we find that distance of separation between molecules in water is closer because the strength of the bond between water molecules is stronger. How do you know this? Because the specific latent heat of vaporization is much bigger compared to petrol. Okay, so this is a very important thing. The numbers tell us, the numbers tell us whether the distance, whether the molecular bonds is stronger or is not. Okay, the numbers tell us whether the strength of the bond between the molecules is stronger. Same thing, whether it is solid or whether it is liquid. Okay, whether it is solid or whether it is liquid, like what we saw just now, the numbers tell us how strong the bonds are. Okay, Bernardine, can you give me the relationship between the specific latent heat and the strength of the molecular bonds? Sorry, what am I saying? Yeah, the strength of the bond between molecules. What is the relationship?
The greater the latent heat of, the greater the specific latent heat, the greater the molecular bond.
Okay, the greater the molecular. Okay, let me see. Hold on. Okay, I will accept that. Actually, I think it works the other way. Because it would be the greater the bond, the greater the heat that you need to break it up. I would say that it should be terbalik lah, kan? Yeah, because it is the heat that breaks up the bonds. So you need to know how strong the bonds are first before you provide the heat. So the greater the molecular bonds, the greater the latent heat lah. Okay, doesn't matter whether it's vaporization or fusion. Okay, so that's another good skill that you have to learn. Very good. Okay, stating the relationship. The greater the bigger the, okay, the bigger the smaller. Those are all important things that you need to train yourself as we go along. Okay, let's look at this. So why are the values different? Okay, uh, I'm not sure whether this is in, but I'm just going to give it to you. So in latent heat of fusion, notice ice and water is basically the same thing. Okay, but take a look at this. Ice is only 3.34 times 10 to the power of 5. But water is 2.26 times 10 to the power of 6. Okay, so the latent heat of vaporization is bigger than the latent heat of fusion, even though the material is the same. It is all H2O. And ice and water is all H2O. Specific latent heat of fusion, sorry, I don't know why they wrote this thing twice now. Okay, so the values are different because in the latent heat of fusion, the energy is only so that they can move, so that the molecules can move like liquid. Okay, the energy is given to the molecules so that they can move freely as in a liquid. So it's just only to break the molecular bonds. Okay, specific latent heat of fusion is only just to break the molecular bonds so that they can become like liquid. Okay, a little bit further apart, but not too far. Okay, but in the latent heat of vaporization, a large amount of energy is needed because number one, you need to separate the liquid molecules to become gas molecules. So, okay, so it is the liquid molecules is already not so near lah. Okay, and now you want to make it to become like super far from one another. Okay, so that is this one. And then the second one is we need some more heat to overcome the atmospheric pressure so that they can move around like gas. Okay, so that's why there's more, even though the material is the same, the latent heat for vaporization is generally for any material, the latent heat of vaporization is always bigger than the latent heat of fusion. Okay, because the latent heat of vaporization is needed to do two things: break the molecular bonds and help them so that they can move even more freer. Okay, they have to overcome the atmospheric pressure, okay, which is the pressure that is all around us. Okay, so that they can move around as gas molecules. So before we continue, sorry, before we continue, I want to share something with you all, which I thought is very interesting. I'm not sure whether you've seen this before, but I saw this again very recently, and I thought, oh, okay, I must show this to you all, just to give you an idea of this molecular bonds thing. Okay, if you've watched this before, I'm sure you will know what it is, but if you haven't, let's watch this together. Okay, let me know if you cannot hear the audio. Okay, so I don't know. Yeah, so no, I know. So at first, like when you're watching, it's like what is happening, right? So at first, when I was watching also, I was like, this was years ago, lah. This is a very old ad. Okay, and I don't know how many of you have watched this. But when I watched this again very recently, lah, and I thought, oh, what an interesting analogy to talk about the molecular bonds between molecules in a solid state. Kan? So, they were all holding hands together, and, it takes a lot of effort. Okay, it takes a lot of effort in order to break them. And you notice that there was only one situation where they were almost broken, which was the earthquake situation. One of them almost fell off, right? Okay, one of them almost fell off. But simply to say that the specific latent heat of vaporization or specific latent heat of fusion, this will be fusion because it's solid to liquid. So the specific latent heat of fusion, it is, it is a lot of energy that is needed to break the molecular bonds. Okay, and if you saw just now, the only amount of energy that could even try to break the bond between the roofing tiles was the earthquake energy. Okay, even the fire just now also wasn't enough. Okay, it was the earthquake. There's a lot of energy to break the bonds. So I hope the video gave you an idea, okay, of what I mean when I talk about breaking the bonds between the molecules. Okay, especially in a solid state. When they're in a solid state, they are very close to one another. They're very tight. Okay, but because they're very tight, it is also easier to break them compared to liquid. Liquid to become gas, because they're so far apart, right? Okay, it takes more effort to break them because they're already so far apart. You want to break them even further apart. There is more effort that is needed there. Okay, so I hope that that short advertisement over there okay, gave you an idea okay, about these molecular bonds. But now let's come back to what we're supposed to do, which is our work. Okay, so now we come to the calculation part. Okay, the calculation part that involves specific latent heat. Okay, now these are a few tips that is given. So when the heat is added or removed, if it is changing the temperature, then we're talking about this. Q equals to mc theta. C is the specific heat capacity. Okay, when the heat added or removed changes the phase of an object, changes phase at constant temperature. They must tell you whether it's constant temperature. Then we use Q equals to mL. L is specific latent heat. So whenever we face a question, the first thing we must ask ourselves is there a change of phase or is there a change of temperature? It cannot be both at the same time. It can only be one at a time. Okay, now if it is supplied by an electric heater, okay, which they give you the power and the time, so we use this same one okay. Previously we looked at PT equals to MC theta or MC delta theta, same thing, because PT is also another way to calculate heat energy. Okay, and all heat energy, whether you use PT ML MC theta okay, all heat energy, the unit of heat energy is always joule. Okay, no need to think so long and so hard. All energy is always joule. Okay, different ways of counting the same thing. Okay, so have this in mind when we are doing our calculation questions. All right, number one. So if 2 kg of ice melts when 452,000 joules of heat energy is supplied to it, what is the specific latent heat of ice? Okay, question we have to ask, is there a change in temperature? No, there is no change in temperature. So we're talking about Q equals to mL. Question is asking for specific latent heat of ice. Means we want to find L bahkan. Okay, can you try this?
226,000.
Okay, unit? It's Q over M. Q over M. Think about it. So what is J? What is Q? What is the unit for heat energy?
Joules.
Okay, joules. And then over M?
Joules over M. Per kg.
Okay, joules per kilogram. Okay, so we write the per in this way lah. Thank you.
Okay.
All right, so 226,000 joules per kilogram is the this one. If you ever get confused, don't worry lah. Okay, use the units individually to get the combined units. Okay, now let's take a look at this. Immersion heater supplies a heat at the rate of 50 joules per second to an insulated vessel containing a liquid. The liquid is brought to a boiling point and kept boiling for 2 minutes. Okay, during which time the mass of the liquid lost is 40 grams. So what is the value of the specific latent heat of vaporization of the liquid? Okay, so this is a very important thing. A lot of information here. But what you need to know is number one, this 50 joules per second refers to power. Okay, power is 50. And if you have an immersion heater over here, you know that you're talking about power times time. But the time given is 2 minutes. Okay? And if you remember from our slide just now, I said time must be in seconds. So we're talking about 120 seconds. Now, during which time the mass of the liquid lost is 40 grams. What does this mean? This means why is the liquid lost? Because the liquid has already changed to gas or steam lah. Okay, that means you're talking the mass of the liquid that changed to steam is 40 grams. So again, the question that we must ask ourselves, is there a change in temperature here? No, there's no change in temperature. That means we're only talking about latent heat. Okay, because there is a change of phase. Okay, so what this sentence is not telling you, mass of the liquid lost is 40 grams, is how much liquid has become gas. Okay, notice how they change the words to test you all, to see whether you understand now, whether you understand what this sentence means. Mass of the liquid is lost because the liquid has already changed to gas. Okay, so the mass is 40 grams. I'm saying grams. Why? Why do I say gram? Very important. Okay, power is 50, time is 120 seconds. My question is, what is the value of L? Okay, so we use PT equals to ML. Okay, calculate the value of L, please. 150. Wow, 150 is a very small value though. Okay. Of course, you put the 50 over here and then you put the 120 over here lah. Okay, there's a reason why I kept mentioning this 40 gram. What should you do to this 40? It cannot be 40 because this is in grams. What should you change this 40 into? You should change it to kilograms. So the kilograms will be 0.04. 0.04. Okay, then you find the value of L. Okay, 150 is a little bit too far though, I think. Okay, so, and I would suspect that the reason why you got 150 is because you didn't change this to 0.04. Okay, it should be 150,000, okay, joules per kilogram. Basic fundamental, okay, everyone, basic fundamental is making sure that your unit, okay, follows the system international, the SI unit. Okay, they may give you gram, okay, and it looks very easy at first sight, but actually it is meant to test you. Okay, just to make sure that you know the very basic skill of changing grams to kilograms, making sure of this. All right, very good. Okay, so 150,000 joules per kilogram. So Vivian, you're on the way there. All you have to do is just probably change the grams to kilograms. Okay, let's take a look at this. So ice cubes of mass 50 grams, everybody, okay, at 0 degrees Celsius is heated by a 50 watt, okay, 50 watt immersion heater. It takes 5 minutes to melt completely. What is the specific latent heat of fusion of ice? This is the exact same question as the one in number 2. Okay, so PT equals to M times L. Okay, but be very, very careful, everyone. Be very careful about the units of each part. Okay, take some time to answer this, please. What is the answer for the value of L? 300,000 joules per kilogram. Okay, I would say that I think you're correct lah. Okay, 300,000 joules per kilogram, or you can give your answer in standard form. Okay, either way also can lah, doesn't matter. Of course, this one looks nicer lah, neater, 3 times 10 to the power of 5. All right, very good. Now, let's talk about this. Question now is asking how long. How long means we want to find the time. Okay, how long means we want to find the time. So the same thing, again, we ask ourselves, is there a change in temperature here? Okay, in the situation, there is no change in temperature because it just asks to melt only. Melt, and it is already at 0 degrees Celsius. No change in temperature. Okay, so we're talking about the same thing. PT equals to ML. L is given, M is given. Okay, power is given. Power is this one, 500. Okay, calculate the value of T, please. Maybe I should ask Iril again, although I think. Can I explain again question 2? Okay, the rest of you answer question 4. Let me go back to question 2. What about question 2 that you want to understand? Do you not understand, Raman? This one, PT equals to ML bahkan. Okay, so if I put the P over here, 50 times 120 equals to 0.04 darab L. So 0.04 saya bawa pergi bawah. 50 times 120 divide by 0.04 equals to L, which is the same thing as here lah. Don't worry so much about this lah. This one is, is cara dia orang buat lah. But if you put it into the formula, okay, dan kau pindahkan dengan betul, you should be able to get this step. Okay, let's go back to number 4, everyone. Question is how long? You can give your answer in, I think the answer will be in seconds lah. I don't think it will even be like 1 minute. 10020 seconds. Oh, really? That long? Okay, let's okay, let's give it a try. So assuming that number 1, okay, 1.5, this is all given lah. Okay, so all you have to do is just substitute. So my question is, how do you get the extra 0 behind there? 1,002 seconds is probably believable, but 10,000 seconds? How do you get the extra 0? 3. Oh, the power. Why? What about the power? Is this not correct? (1.5) times 3.34 to the power of 5 divided by 500. 1002. Our module is power of 6. Oh, okay, fine. Okay, so actually, technically, Chloe, you were doing it correctly. It's just that the module got mistake lah. Okay, it should be 10 to the power of 5 because it's only ice. 10 to the power of 6 is usually liquid to vapor. I mean, vaporization lah. Okay, very rarely we find specific latent heat of vaporization fusion to be 10 to the power of 6. Okay, so yes, please change the module to power of 5, and of course the answer is 1002. So anyway, good job, Chloe. Okay, at least you attempted. Okay, and you got the answer. Good for you. All right, let's go to question number 5. Okay, now 500 watts electric heater. Same thing. Whenever you see electric heater, you know already. Sure, PT one. Don't need to think so much. Okay, used to boil water. What is the time required to reduce the mass of 70 grams after the water has reached the boiling point? So again, no change in temperature here. Mass is given, specific latent heat is given, power is given. We are once again looking at how to find the value of T. Okay, give this a go lah, everyone. My main job today is just the calculation question. So if I can cover all 7 today, hooray for me.
316.4.
316.4. 316.4. What is the unit? Time.
Seconds, I know.
Okay, seconds. Okay. So there's this famous meme that's going around, right? Physics teachers will always ask you, what is the unit? What's the unit? Okay, and usually in my class will be 316.4 what? Ringgit, cent. Okay, so please make sure you get the unit correct lah. Okay, I think it looks correct. Okay, very good. So same thing, we use the same formula. Make sure to change the 70 grams to kilograms. Okay, all right, good job. Now we come to the slightly more difficult ones, which involves both specific heat capacity and specific latent heat. So you have 0.5 kg of water at 30 degrees Celsius is heated until it is converted to steam. Okay, let's consider again, if the graph is water to steam, that means it will be like this, like this, like this. Remember from the heating graph? Okay, from the heating graph, you have water at 30 degrees, okay, like this lah. So water and then change in phase, and then after that it becomes steam. Okay, so you need to take note of the heating curve. That's why we learn the heating curve first, so that it helps you. Okay, so water originally is at 30 degrees Celsius. It must go until how many degrees Celsius before it can become steam? Who knows? How many degrees must it become? Okay, it must become 100 degrees. 100 degrees water. Okay, then over here is what? This is specific latent heat. And then at the end over here is 100 degrees steam. Okay, so it must become 30 from 30 degrees Celsius water, kasih panas, 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 panas until it becomes 100 degrees Celsius water. And then kasih panas, 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 panas so that it can become 100 degrees steam. So use the heating curve or the cooling curve to help you to understand what is happening. That's why they give you these two values, What is the amount of heat energy supplied to it? You need to count, you need to count the specific heat capacity involved here plus the specific latent heat involved here. Okay, you need to count these two. Okay, so let's do this separately. Okay, I want all the guys lah. Okay, guys, I want you to count the specific heat capacity. Okay, Q equals to MC delta theta. And all the girls, I want you to count the specific latent heat, ML. Okay, the mass is the same, 0.5 kilograms. For the guys, you need to consider what is the change in temperature. 30 to 100 degrees Celsius is how much change in temperature. Okay, so calculate this according to your own gender, and then after that, I'm going to call two different people to give me the values. Okay, what is the specific heat capacity for this, and what is the specific latent heat for this? Okay, 1 minute now. Let's have, wow, Trevor so fast. 1-4, okay, fine. How come Trevor, you know that I'm going to call you? Actually, I wasn't going to call Trevor, but since Trevor answered, 147000. Okay, can I have Meryl for the latent heat? 147000. Meryl, latent heat please. 113 and 4 zeros. Okay, 113 and 4 zeros behind. Okay, again, notice you are hitting the same thing, Okay, but take a look at the specific capacity. Only 6 digits, but the latent heat, oh my goodness, it is 7 digits, 130,000 joules. Okay, it's a lot of heat to why? Because water to steam, you have not only you have to break the molecular bonds, you also have to give them enough energy to overcome gas pressure so that they can ignite. Okay, so let's double check. Okay, 14700, and then the other one is 11300. So the question is, what is the amount of heat energy, right? So you have to total this together. Okay, and you will get 14700 plus 100 and 1,130,000 joules. So you get 1277000. You add these two together. Okay, so use the heating curve to help you to understand which heat that you want to use. Anything with the increase of heat is specific heat capacity. Anything with no increase of temperature, okay, but change of state is specific latent heat. Okay, then after that, the total amount of heat is, you visualize this together. Okay, let's do one last one. This should be question number 7, right? Why is it question number 6? Okay, 3.2 kilograms of water is 28 is heated until half of it changes to steam at 100 degrees Celsius. Okay, so first of all, same thing, water at 28 becomes water at, so water at 28 becomes water at 100 degrees Celsius. Then after that, it becomes steam at 100 degrees Celsius. And then it has to change half only, half of it changes to steam. So actually not all of it changes to steam. Okay, so you need to be careful about the specific latent heat of vaporization. The mass is slightly different here. Okay, so again, the same thing. Let's split this up. Now I want the ladies, please count the specific heat capacity, and the guys, I want you to count the specific latent heat. Take note of this, half of it changes to steam. Okay, I want you to be very careful with this. Okay, so girls take the MC delta theta, and then guys take the M times L. 3616000. Really? Half the this one, or Joey, the first one? 309120. Looks about correct. 309120 joules, no joules per kilogram, because it's just heat. Wait. 295680. Wow, now it's another difference. 295680. Okay. Almost the same lah, kan? But okay, let's see. So we have all this. So actually it's 967680. How do you get 295 though? Oh, okay. Why is it 72? Because 28 degrees to 100 is 72 degrees. The change in temperature is 72 degrees. Okay, 967680. Is that correct? Yeah, 967680. Okay, so take note where you made the mistake. All right, now Wong's part is 1.6 kg of steam. Okay, so it should be 3616000 because we only need half of it to turn into steam. Why do we need half of it to turn into steam? Because the question asks for half lah. Okay, so we need to understand that. Okay, so the total amount of heat will be these two added together. Okay, it will give us 4,583,680 joules. Again, you notice the specific heat capacity value is always significantly smaller than the latent heat value. Always the latent heat value is very big. Okay, always notice this. All right, so what I want you to do today is I want you to answer question number 1 to number 12 in your just the objective questions. Is it number 12 or number 13? Oh, sorry, question number 1 to number 14. Okay, question number 1 to number 14 in the tutorial question. Okay, tutorial 4.3. It's just objective question lah. Okay, so please answer this, and then the first thing we will do on Wednesday is we will discuss these 14 questions.